To begin with the key learnings, the first principle includes the GND density control via hat spacing. In the first paper, they have discovered that the hat spacing to the width ratio have when varied from 0.14 to zero point 0.5. They saw a 90% increase in the GND density. For our refractory alloy, we have kept the hat spacing to the width ratio less than zero point 0.3 for sufficient dislocation density introduction and subsequent microstructure control. The second principle includes the chemical homogenization via remelting. They measured that for chromium segregation saw a reduction from 2.7% excess to a 0.9% excess, which is a 67% reduction. And for molybdenum segregation, it was observed that it was reduced from 1.4% to 0.7%, which is a 50% reduction. So the dramatic improvement in the chemical homogeneity allowed complete recrystallization through subsequent treatment. The thermal stability programming comes to the third principle, which includes the controlling of or programming the material through two factors, which includes GND density through hat spacing and chemical heterogeneity via remelting. GND density acts as a driving force for recrystallization, while remelting acts as removes the pinning points that prevent grain boundaries from moving. The fourth principle comes as a solidification temperature range, where we have also used the genetic algorithm approach by calculating the STR or the solidification temperature range for each composition using thermodynamic software, keeping only compositions with STR less than 61 degrees centigrade, making the best composition to create the new ones and replacing repeating for multiple generations. The fifth principles includes the in situ precipitation optimization, where it is nothing but the product of the volume fraction of precipitates and the driving force. They have tested for 17 for precipitation hardened stainless steel, where the precipitation strengthening factor was 44 joule to the power half. So they have tried to optimize the composition to a value less than 44 joule to the power half. We choose the tungsten, tantalum, and copper. The reason we are choosing just tungsten is the backbone of the alloy. Tungsten has the highest melting point of all metals, which is 3,400 and 222 degrees centigrade, and excellent high temperature strength. Its thermal conductivity is around 173 watt per meter Kelvin. It's crucial for dissipating heat from plasma spacing surfaces. However, pure tungsten is brittle and difficult to process. By alloying it, we can improve its processability while maintaining its beneficial properties. The next comes in the tantalum, which is the toughener. Tantalum has a very high melting point, which is 3017 degrees centigrade, and is much more ductile than tungsten. It forms solid solutions with tungsten, meaning atoms mix randomly in the crystal lattice rather than forming brittle intermetallic compounds. The 30% tantalum content provides substantial solid solutions, strengthening while maintaining good ductility. Then comes the copper, which serves three critical functions. Copper has a low solubility in tungsten and tantalum, so it will precipitate out as fine particles during cooling or heat treatment. Thermal conductivity next comes in, which is copper's excellent thermal conductivity, which is around 400 watt per meter Kelvin, complements the tungsten matrix. Next comes in the copper overall lowers the melting point and provides and improves laser absorption during printing. Then comes in the chromium and the nickel, which forms the process aids. These elements provide oxidation resistance and help control the solidification behavior. Nickel in particular can promote austenite formation during solidification, which then transforms to martensite during cooling, providing additional strengthening mechanisms. Why not choose the other alternatives, which include the molybdenum and niobium and the copper alloy system? Because molybdenum and niobium are good refractory metals, but the lower thermal conductivity than tungsten. Molybdenum has around 138 watt per meter Kelvin compared to the tungsten, which is around 173. The lower melting points and the less established for fusion applications. For the second alternative, which is molybdenum, rhenium, and copper, it is because rhenium is excellent for ductility but extremely expensive. Supply chain challenges and overkill for many applications. To have the certification path analysis, we calculated that our tungsten, tantalum, and copper alloy begin solidifying at 2480 degrees centigrade, which is the liquidus, and the complete solidification at 2435 degrees centigrade, which is a solidus. Has an certification temperature at a range of 45 degrees centigrade, which is well below the 61 degrees centigrade mark. Partitioning behavior, we see that the partitioning coefficient tells us how elements distribute between solid and liquid. For copper, it was zero point 0.8, which means copper refers to the liquid phase, prefers the liquid phase. For tantalum, it was 1.1, which means the tantalum prefers the solid phase, and 0.95 for tungsten distributes almost equally. This why this partitioning coefficients are good is because copper's preferences for liquid means it will be available for precipitation later. No extreme partitioning that would cause even segregation, and relatively uniform distribution of major elements. Go criteria are as follow that the solidification temperature range has to be less than 50 degrees centigrade for hot crack prevention. The liquid films are continuous, can form along grain boundaries. The solid skeleton is not strong enough to resist the stresses. The solidification range is wide enough that significant stresses develop before solidification completes. Why 50 degrees centigrade instead of 61 degrees centigrade? In paper B, we found that the 61 degrees centigrade was the threshold for 17.4 pH steel or the precipitation hardened steel. But refractory alloys, we have higher melting points, so thermal stresses are greater. Often have poor ductility at high temperatures, may have different weighting characteristics of liquid films. Our 45 degrees centigrade solidification temperature range provides a comfortable safety margin. Next comes the solubility of copper in the matrix, which is larger than 3%, avoiding excess copper segregation. The liquidation cracking mechanism is that if copper has very low solubility in the solid, it will be forced into the remaining liquid during the solidification. If the copper concentration in the liquid becomes high enough, it can form low melting eutectic phases that remain the liquid until much lower temperatures. The danger of copper-rich liquids is that have very low strength, weight, grain boundaries effectively can cause severe cracking under thermal stresses. Next comes in the no brittle phases below the 20% solid fractions, which is that why 20% threshold is because it forms continuous network through the microstructure, creates easy crack propagation paths, and significantly reduce the ductility. The thermocal verifications criteria are as follows, which includes the target value and the calculator and the status. For STR, it has to be less than 50 degree, calculated was 45. For copper segregation, it has to be less than 2, it has calculated to be 1.8, and the brittle phase temperature has to be larger than 100, 1000 and 200, 1200 degrees centigrade, and it was calculated to be 1350, which is a go. The thermodynamic databases include the TCNI8 plus the MOBNI4 for the validation for the refractory systems. Copper diffusion parameters have been verified. Powder specifications. It includes the particle size distribution, which has to be between 25 to 45 micrometers for T50. Too small cannot be accepted because of the poor flowability, oxidation risk, handling hazards, and poor spreading. It cannot be too large, like more than 60 micrometers, because of incomplete melting, the rough surface finish, and the poor resolution. It has to be somewhat like a between range of a Gaussian distribution, like from 15 to 53 micrometers. Mono-size powders don't pack well, like stacking marbles. A size distribution of allows smaller particles to fill the gaps between the larger particles. This improves the package density from 50% to 60%. Better packing means less shrinkage and better dimensional control. The powder morphology includes the sphericity to be larger than 0.85 because of the flowability. Spherical particles roll past each other quite easily. Because of the packing, spheres pack most efficiently. And coating, non-spherical particles can interlock and cause streaking. Next comes in the chemical purity, which includes the oxygen to be less than 100 parts per million, because oxygen forms oxides from oxide inclusions that act as stress concentration and crack initiation sites, impair metallurgical bonding between particles, can create brittle phase at grain boundaries. Nitrogen has to be less than 50 parts per million. Nitrogen can form hard, brittle nitrides that reduce toughness, provide sites for crack initiation, can interfere with precipitation strengthening. The build setup includes base plate selection, which is tungsten as a base plate because tungsten has similar coefficient of thermal expansion to a tungsten, tantalum, and copper alloy, which is around 4.5 10 to the power minus 6 per Kelvin. High temperature strength won't deform under processing conditions, and the compatibility because they won't react with or contaminate the build material. The tantalum interlayer, because this serves as a sacrificial layer that prevents diffusion bonding between the part and the base plate, allows easy removal of the finished part, and accommodates any minor coefficient of thermal expansion mismatch. Preheat strategy. The thermal stress problem is that in additive manufacturing, without preheat, you have a huge temperature difference. The melt pool has to be around 2500 degrees centigrade. The surrounding material has to be around 20 degrees centigrade. And this 2480 degrees centigrade difference creates enormous thermal stress. The strategy of it. The parameter selection rationally includes the laser power to be between 200 to 400 watts. The lower bound 200 watt must provide energy to melt the refractory metals for high melting points, overcome the reflectivity, create a stable pool. The upper bound of 400 watt is limited by the vaporization risk, keyholing, machine capabilities, and the scan speed too has to be around 600 to 1200 millimeters per second. This controls the solidification conditions, which includes the slow speeds for 600 millimeter per second, higher energy input per unit length, deeper melt pools, slow cooling rates, large microstructural features. What we expect. For the first speeds, which is around 1200 millimeters per second, low energy input, shallow mill pools, faster cooling rates, and finer microstructures and higher productivity. The hat spacing has to be around 60 to 120 micrometers. Based on paper A, the hat spacing to the width ratio principle. Assume melt pool width is around 200 micrometers. For refractory alloys, the target hat spacing to the width ratio is around zero point 0.3 to zero point 0.6. Therefore, we must have around 120 micrometers of batch hat spacing. The layer thickness has to be around 30 to 50 micrometers. Thinner layers like 30 micrometers provide better resolution and surface finish, more consistent melting, longer build times. Thicker layers like 50 micrometers have faster builds, higher productivity, and risk of incomplete melting between layers. The advanced strategies include remelt strategy, which provides remelting every layer, doubles build time. Too much remelting can cause excessive heat buildup, and the biggest homogenization benefit comes from the first remelt. The track overlap ensures complete melting between the tracks, no unmelted regions, and uniform microstructural development and consistent mechanical properties. Then of experiments include low power, low speed, which is 200 watt and 600 millimeter per second. The low power, high speed, which is 200 watt and 1200 millimeter per second. The medium power, low speed, which is around 300 watt and 600 millimeter per second. The medium power, high speed, which is 300 watt and 1200 millimeter per second, and the high power low speed, which is around 400 watt and 600 millimeter per second, and the high power high speed, which is around 400 watt and 1200 millimeter per second. These six build approaches are required for the design of experiments. The kill switch implementation includes the crack detection for larger than 1 millimeter per square, one crack per millimeter square, visible at the 50 times magnification. We need to stop. The density has to be less than 98% measured by the Archimedes principle. The spatter is excessive spatter affecting next layer. We should reduce the power, and delamination for any layer separation. We need to increase the preheat. Success criteria for the method of optical microscopy, our parameter will be the crack density, which has to be zero cracks per millimeter square. For the Archimedes principle, we need to check the density. For the electron backscattering diffraction, we need to check the parameter of texture or the cell size. For the energy dispersion spectroscopy line scan, the parameter will be the segregation index, which has to be less than 15% of variation. For the micro hardness, the parameter will be the hardness map, and for the bend test, it will be the ductility, which has to be greater than 10 degree for the bend angle. The quality gates include no visible cracks, and it will last larger than 98.5% density, the homogeneous microstructure, and the minimal segregation. And it should meet the target hardness and the bend ductility. This comes in the risk assessment and the countermeasures. For the risk, first risk includes the copper risk segregation and the liquidation cracking. Why these liquid films are dangerous? Because they cannot support mechanical loads when thermal contraction stresses develop during the cooling. These weak liquid films tear open, creating interangular cracks. What is our mitigation strategy for this? It is that we need to have the composition control, that is having the solidification temperature range less than 50 degrees centigrade ensures the mushy zone is narrow. Remelting gives copper a chance to diffuse away from the boundaries. The cooling rate control, by which we mean that keeping it in the 500 to 1000 Kelvin per second, optimization between segregation and cracking. And the grain refinement. Fine grains mean shorter liquid films and that are less continuous. Risk two includes the second risk includes the insufficient high temperature strength, which is why the precipitates might not work, because copper precipitates can coarsen, which is called the Oswald ripening at high temperatures, dissolves back into the matrix and lose coherency within the matrix. Next comes our mitigation approach for this includes the optimized composition, maximum precipitation driving force, in situ aging, which includes using built-in heat treatment during printing, microalloying, which includes the boron and zirconium segregate to grain boundaries, strengthening them, and processing control, which is including the fine cellular structure, provides additional strengthening. The backup strategy includes that post-build aging at 600 degrees centigrade for 2 hours would ensure complete precipitation, optimize precipitate size and distribution, and provide a known reliable strengthening method. Next comes in the TICTRA simulation parameters. The database is as it is the TCNI8 and the MOBNI4. The temperature profiles based on the operando measurements in the paper A, and simulated elements include copper, chromium, diffusion in the tungsten and the tantalum matrix.